This is Denver 2000.
Pretty much you always have 2000. You're not pushing the data fast enough.
And this is our 4-voice monophonic digital synthesizer.
So we're not getting changes.
We have control over each oscillator independently volume. We have a choice of 3 different waves. You can choose a sawtooth, a square, or a triangle. And you can also tweak the frequency for each oscillator individually. We have it set up to the scope for the different
push the change.
The different frequencies. Yes. It uses a MIDI controller, a UART to get serial MIDI data. That is sent to the processor, which gives the hardware oscillators the period of the wave. And those 4 oscillators are summed together, and you have a sound.
Figuring that out pretty much was most of our error. Yeah, well, not even quite that. It was, yeah, but the byte order was wrong. So I guess I didn't pick anything. It was sending the bottom half of the byte first, and then we were checking the upper half of the byte first.
So yes,
and we changed the assembly.
Synthesizer 2000. Thank you for playing.
Numbers,
an image, and transmit it over to our little processor here.
All right, ready?
Go. You're already going.
There we only got Dario.
Yeah, well, it doesn't reach that.
You're gonna have to wait about 5 minutes for your next chance to get a picture.
It's okay, your eyes are closed. We'll apply an effect, no one will ever notice.
We'll apply an effect, yeah. That's her.
So yeah, once we transfer it over to the onboard computer, then we have about a dozen different filters and effects that we can apply to the image.
Mine are close.
Reliable.
Finishing up here.
Alright.
So now that the image is completed, we can cycle through and pick different effects that we want to apply. Here we think we have just a blue overlay. This is an 8-bit pixelization, kind of like a NES kind of effect.
Here we go.
Some more pixelizations.
We don't want that one. Oh, that one's not bad.
Kind of some photo book, is that what Apple calls it? Instagram kind of applications.
Sure, go for it.
Some more blues,
some
greens.
Liney green, liney red.
That one's good. That's good.
Lighter creepy.
Lighter creepy, yeah. I think that's our dark creepy and our light creepy. Our negative creepy.
And
then 3-bit color.
Yeah, that just makes it look like... Let's just send the plane.
There you go. You want that one?
Yeah, send that one.
Send that one? Alright, and so after they've picked the filter, the chip applies the filter that we chose and exports it back over to the computer where we can save it as a JPEG. Oh, one more. There we go.
So this part's kind of boring, but these 2 flashing lights are just kind of showing us that it's actually sending all the data over.
Believe it or not, this is hard.
And then once those are done, the actual JPEG is created basically.
I know you've been using Java.
Yeah, Priyanka's like,
I built a remote GPS locator that utilizes a cell phone to calculate the X and Y, or to calculate the actual position on the screen. And we utilize the 4G data to get a reliable connection to the PC, which then sends it to our FPGA board, which then performs the actual calculation of where he would be on the screen. We're waiting for him to actually get outside where the image will show up, because right now he's not sending any information right now. So we're not seeing most of the data. Many limitations is that the GPS on the phone does not push an accurate enough or fast enough changes through the system for us to see a very consistent movement pattern on the guy. So we get a kind of a choppy jumping motion that happens. This is just due to the limitations of the phone and the fact that we didn't have direct access to the GPS information. We were using the .NET framework.
So we had to undo it.
It seems like it's starting to push the data now. So with the GPS accuracy, it starts off with probably only about 1 satellite, and that can give us anywhere between 3,000 to 350 meters of inaccuracy. And so until he pushes until it gets and acquires a couple satellites, you don't ever see the guy because the phone's just guessing on where he's actually located. Text him to restart the service.
Monitors, not us.
We don't have
Ours
his
are actually
number.
pretty.
No, text him with your phone to restart the service. Oh, there it goes. So there, it picked it up now. So, and the phone sends the GPS data that it has cached, or the new GPS data every half a second. So it's less of the issue of the phones sending the data or of the GPS limitations.
As far as you know, that's a life.
The phone itself, not pushing more data. I don't know why. I don't have a low enough access. It's not pushing it. It's going to change every purpose or something. Because the map application, so data much more frequently. Much more active. We can't get to yeah, they're all
Oh, you saw how bad I did yesterday? Oh, where's the key?
Music scales are 8.
Leandra had to work for half an hour to fix what I was doing, like 3 seconds. Yeah, but does it calm down? I want to get that speed up, huh? Get it to level like 9, maybe.
Yeah, like Western scale.
The challenge you guys is leveling.
That one happens to have some. It happens to have 8. And so there are a few like there's Chinese scales and stuff. Yeah, so there's different. How are you?
Every half a second.
Hey!
Pacman game. We designed our own processor and all the hardware for it, all the I/O. We made our own assembler and programmed this from assembly code.
Which totaled up to about 8,000 lines of assembly code that we packed together.
The processor is a 16-bit CR16 architecture, 50 MHz clock, and we have 16K of RAM. Well, actually, no, we've got 32K of RAM because we've got 2 bytes per. Anyways, it was a great fun project. We made a bunch of support software like scripts that generate our glyphs automatically because we have over 400 different glyphs that we've defined in hardware in our project, and those were all generated procedurally with a MATLAB script, such that we didn't have to hand code them. The Verilog file that generated wound up being 37,000 lines long.
You changed the scale of the scale.
You'll notice in this version of Pacman, he tends not to eat too much. His pills remain.
He's on a diet.
Exactly. He's on a diet. He's very passive aggressive today as well, and so not much interaction with the ghost. But after all, if you walk into a ghost, what's going to happen? It's going to pass right through it anyway. So we felt this was a more realistic implementation. But really, the truth is, we've got an update coming.
Yeah, and then we just have
Soon.
So what we have here is just a random, pseudo-random pattern musical generator. So in a first phase, we can have input where we have this cursor on the keyboard that we can put down squares.
Everyone's a winner.
Or these arrows, rather.
Is a winner.
We can kind of sit and rotate them and create kind of a visual pattern. Then, when we start the program, these move along the grid. When they hit the sides of the grid, they make a sound that corresponds to where they are. And
So
if they hit one another, they turn clockwise.
Pacman is on one of these docks.
So we can kind of create these, kind of patterns, pseudo-random patterns of music. Something else we can do is we can change the musical scale over here on the switches. Okay, so right now we're doing a major scale. This changes it to be a minor scale. It's hard to tell.
There's a statement that says, okay, there's a ghost, and Pacman dies, and you lose one of these guys. You just lose all of one, or roller snake. And this is kind of like docile.
So that changes the scale to something. It changes these tones to something different when the wall happens. We can also change the root note of the scale. So we basically shift the scale up by a certain amount.